All right, I'm making a video to explain post-class assignment problem number 9 for 9C, number 1. Okay, so this question is written here. You'll have different numbers in your particular version of the problem, but you can see the numbers that I have here. So a meter stick has a mass of 15 kilograms and balances at its center. So let's draw a picture of this initial state. We've got our meter stick. It balances at its center. It's 1 meter long. And it has a mass of 0.15 kilograms. Okay. Now, the final version is we've still got a meter stick. We've got a chain suspended from one end. And now the balance point moves 16 centimeters toward the end with the chain. So our new balance point is here. This was our old balance point. And this distance is 16 centimeters. Okay. And we want to know what is the mass of the chain. Okay. So how can we solve this? This is a static equilibrium problem. All right. And for static equilibrium, we know that our first step is to draw all the things that are exerting forces and sum the net torques to 0. Okay, and we know that we can treat each the force of gravity as acting at the center of an object. So let's draw a free body diagram. I'm going to draw the second state over here bigger. Okay. So we've got our chain here. And we've got two forces on the meter stick. We've got mass of our stick, G here, acting on the center of mass of the meter stick. And then we've got M chain G here. Okay. And then we've got also a normal force from the balance point that's acting upward. Okay. Now, we know that the sum of all our torques is equal to 0. And we want to do this we can pick our rotation point to be anywhere that we want in a static equilibrium problem. But in a problem like this, I think it makes most sense to put our rotation point, or our axis of rotation at our balance point. So we're going to put it where I just drew this blue X here. I'll highlight that in pink. So that's going to be our balance point. Okay. So now we've got two torques. So one of them is from the mass of the meter stick. That is exerted a distance 16 centimeters from our axis of rotation. So our torque from our stick is the mass of our stick times G times 0.16 meters. Okay, that's our force times our distance. They're perpendicular, so I don't have to worry about the angle, or I can also find that angle. Theta equals 90 degrees. So our torque is F R sine theta. And sine theta equals 1. So here, this is just FR. Okay. Okay, and then we need to find the direction of that torque. That torque from the meter stick is going to tend to rotate our meter stick in a clockwise direction. Right? If you imagine if you had only that force, or if you push harder, it would rotate the stick clockwise around this axis of rotation. Remember that a clockwise torque is negative, so that torque is negative. And then we've got the torque from the chain. That equals mass of our chain times G times the distance to the chain. This distance here. So we know that our stick is 1 meter long. The center of mass is at its center. So that's 50 centimeters from the end, and that equals 16 centimeters between the center of mass and our balance point plus D. So D equals 34 centimeters. So our torque from our chain is mass of chain G times 0.34 meters. We want to find the sign of this one as well. So remember here the chain is exerting a counterclockwise torque, tending to rotate this way around that center of mass. And remember that counterclockwise torque is positive. So our torque for our chain is positive. Okay. So our torque from our chain plus our torque from our stick is 0, and that's equal to mass of our chain, which is what we're trying to find, times 9.8 meters per second squared, times 0.34 meters, minus mass of our stick, which is 0.15 kilograms. Here's where you might have a different number in your problem. 9.8 meters per second squared for gravity, and then 0.16 meters. So I find that my mass of my chain is 0.15 kilograms times 0.16 meters divided by 0.34 meters, and that gives me a mass of my chain of 0.0706 kilograms. All right, that's it for this video. Thanks.